Perfect. So today we have Grisha talking about equivalent models of derived stacks. I'll let you go ahead.
All right. Thank you so much to the organizers for allowing me to present here. Today I wanted to talk about my work with Professor Dmitry Pavlov about equivalence of models for analytic derived geometry. So I will try to specify in the course of the talk what these words mean, but let's start from the general goal. So we're working in characteristic zero, so everything is very simple in a sense. And we have simplitional models of derived geometry and differential graded models of derived geometry. So, I mean, you have, I guess, differential graded algebras and simplitional algebras. And you want an equivalence between the two. Of course, you can put various bells and whistles on both sides. You can consider stacks, which are just kind of homotopical sheaves on some derived side. But the essence of things is pretty simple. You want to have an equivalence between simplicial and DG objects. And today I will try to present the theory needed to establish the category of stacks on a derived side, the category of the necessary tools from algebraic theories necessary to explain what is, I guess, a model of derived analytic geometry in terms of algebras over Fermat theories. And then I will talk about the result itself. So first we'll start from stacks on homotopical sites. We'll talk a bit about simplicial presheaves, homotopical sites, homotopical descent. Then we'll talk about Fermat theories, which are kind of, I guess, schemes on which you can build various types of algebras that have certain geometric meaning. Then we'll talk about monoidal Dold-Kan correspondence, specifically in the context of Fermat theories and characteristic zero. And finally, we'll end with equivalent models of derived stacks, which is the essence of my paper. All right, so let's start from simplicial presheaves. So assume that we have a small category C. We say that the category of simplicial presheaves on C is a category of countervariant functors from C to simplicial sets. And the category of simplicial presheaves has a model structure. And there are, of course, several model structures. There are, in fact, some works dedicated specifically to model structures and simplicial presheaves, mainly, I guess, by Rick Jartin, but there are, I guess, some others too. But in fact, it's not really important which model structure we use. So we will mostly, I guess, use the injective model structure where cofibrations and weak equivalences are defined object-wise, and then fibrations are defined using the right lifting property with respect to cofibrations. I guess another remark that I should make here that if you're more on the side of infinity one categories, then probably it is preferable to replace simplicial sets by your favorite infinity category of spaces. And then in a sense, it even simplifies things because you don't need to care about such things as pre-stacks. You can just go directly to presheaves in a sense that these are infinity functors between your infinity one category C and your infinity category of spaces. All right, so now moving on, we define pre-stacks on relative categories. So assume that we have a relative category, i.e. we have a wide subcategory, meaning that it contains all isomorphisms, and it satisfies the 2 out of 3 property. Then we denote by this CW hat the left Bousfield localization of the category of simplicial presheaves with respect to the image of the morphisms in W under the Unity embedding. And we call this category the category of pre-stacks on our relative category. In the language of infinity categories, the category of pre-stacks, as I said before, is just the category of infinity functors from I guess I should put op here, from the infinity categorical localization of C in W to the infinity one category of spaces. And you can model spaces by anything you want, topological spaces, simplicial sets, or whatever other kind of model you choose, CW complexes, for example. All right. So this was, I guess, sort of a general nonsense. And now we have to introduce a certain geometry into the picture. So we need to consider coverages and sites. So we start from a concept of a coverage. It is slightly more general than the classical definition of a growth index topology on a category. And basically it just says that for each object, we have a collection of families of morphisms, which we call covariant families, such that for any covariant family on one object and a morphism into this object, we have another covariant family on the object Y, such that any morphism in this covariant family factors through some morphism in the initial covariant family. So we have a commutative diagram like this. I guess on sufficiently complete sites, this is just equivalent to saying that our covariant families are closed with respect to taking the fiber products, and then this gives, I guess, a more classical approach to the definition of the growth index topology. But sometimes the sites are not sufficiently complete. So, for example, if you're dealing with the site of Cartesian spaces with good covers, i.e. intersections of open subsets should be always contractible, then you can't form fiber products, but you still can form some finer coverings which satisfy this property. So, but morally, you should think of it as just distinguishing some class of families of morphisms that give a covering of your object. And a site is a category equipped with a coverage. So now we want to consider a homotypical version of this concept. And for this, we take a relative category, we equip its usual one categorical localization with the coverage, and we say that this is a homotypical site. And let's consider an example. So we can consider a category of commutative differential graded algebras over K, where K is, for example, a field of characteristic 0. Then we take the opposite category, and we do this because we want to work with spaces instead of algebras. So we need to take an opposite category. And then we define the coverage on commutative differential graded algebras as follows. So it's a collection of morphisms from BIs to A, such that, first of all, if we take the zero homology group, we obtain a coverage in your favorite topology on the category of usual commutative algebras. This could be either Zariski, Tal, FPPF topology, or whatever you want. And then we additionally require that for higher homology, you have an isomorphism like this. So I guess the higher homological data glues appropriately in this current family. All right, so let's consider hypercovers on homotypical sites. So instead of just usual coverages in the homotypic setting, we need something more general. And for this, we introduce hypercovers. So if in the one categorical setting where you consider sheaves of sets, the descent condition is considered only with respect to covers, then here we need to consider homotypical descent, and this means that we need to consider hypercovers instead of usual covers. So let's consider a category like this. This is a category of homotypical covers of X, families such that they become covariant families in the localization. And we can consider a simplicial object f dot in this category, and we consider its image under the Uneda embedding in the category of simplicial pre-sheaves. Then this thing is called homotopical hypercover of X. And I guess the simplest example we can consider in this case is the so-called check groupoid or check simplicial object. So assume that you have a cover like this, and that your site has fiber products. Then we can form a simplicial object like this. So we have the image on the Uneda embedding of X. Then we have the co-product of images of UIs, then the co-product of images of pairwise fiber products, and so on. And this is a prime example of a hypercover. And in fact, if your site is sufficiently good, it's enough to consider only hypercovers of this form. All right. By the way, if there are any questions, please ask me, because I guess I'm going pretty fast. Yeah. All right. So now let's discuss steps on homotopical sites. So we denote by sheaves on CW the left Bousfield localization of the category of pre-stacks, which, as you might remember, is a Bousfield localization itself in the class of weak equivalences on C. And we localize it in this class L, which consists of maps from homotopical hypercovers to objects of the category. So essentially what happens here is that we define the category of sheaves as the category of objects which have the homotopical descent property, i.e. if we evaluate them on a homotopical hypercover, the result should be the same as if we evaluate them on an object, I mean, roughly. And then we say that this category is the category of stacks on CW. I mean, you should probably write here somewhere the growth index topology you use on the category, but in most cases, it is understood and we omit it. So I guess the framework for this approach is laid out in Toyen's Visossi paper, Homotopical Algebraic Geometry 1. All right.
Quick question here. Like,
yeah.
If you take C to be just the category of schemes, maybe just say over Z or over the integers, what would you usually take W to be?
Yeah, so I mean, if we'd consider just mere schemes, then W would be trivial. It just consists of isomorphisms. But if you consider derived schemes, so you consider, for example, DG algebras over either Z or Q or whatever, then W would be probably the subcategory of quasi-isomorphisms. So the point is to be able to reflect this structure of relative category in the category of sheaves.
You think you'd do a similar thing, like if you had C being like the derived category of a scheme, I guess, like that derived category of quasi-coherent sheaves on a scheme?
Yeah, sure. I mean, you can do something like this, but yeah, of course. So you for example, if you want, you can consider C as the category of of chain complexes of sheaves on a scheme X, and then W would be just the category with the same objects and quasi-isomorphisms as morphisms between objects.
Cool, thank you.
All right. Yeah, thank you for the question. So now let's move on to, I guess, the more concrete part of the talk. namely the theory or the approach via Fermat theories to the analytical geometry. So the main motivation of this approach is that in the case of algebraic geometry, we have this nice duality between affine schemes of finite type and finitely generated commutative algebras. The opposite category of finitely generated commutative algebras is just the category of affine schemes. But what happens if we consider smooth manifolds, for example, or complex analytic spaces? So we know that for affine schemes, if we take the global sections of the structure sheaf on the product, we get the tensor product of global sections. That's great. But as you probably know, if we take smooth functions on R2, it is not equal to the tensor product of smooth functions on R and smooth functions on R, because this is far larger than this. So I guess the question should be, how do we fix this? And the answer is we need to consider a different notion of an algebra. So we need to somehow incorporate information about being able to take compositions with smooth functions or holomorphic functions or something like this. And to set up this approach, we start from the simplest case for which this theory is not even needed. That's the theory of commutative algebras over a commutative ring. So assume that you have a commutative ring R. Then we define the category com_R as follows. So objects of this category are non-negative integers with the property that it is generated under products by the object 1. So object n is just a product of n copies of the object 1. And the morphisms between objects m and n are just R polynomial maps from Rm to Rn. So a model of such a category in the category of sets is a product preserving functor from this category to sets. That's just the definition. We denote this category by this fun with the sign of product from com_R to set. And as you can easily observe, there is a canonical equivalence of categories of commutative R algebras and product preserving functors. Why is that? Well, basically because this category of commutative algebra, this category com_R, just remembers all possible operations that you can do on a commutative ring. So you have your multiplication, but actually you'll have all the polynomials that you can construct. So you can take a polynomial with m arguments, you can plug in elements of the ring, and you can obtain another element of a ring. This operation preserves the ring. So it's quite natural to expect that indeed such product preserving functors give the same information as just commutative algebras over R. And this forms the basis for the approach via Fermat theories. So the Fermat property is an additional property that ensures that an algebraic theory is sort of analytical. So assume that you have a category T with objects also consisting of non-negative integers with the same property that object with index n is equal to the product of n copies of the object with index 1, and assume that you have a functor from commutative, from the category that encodes commutative R algebras into the category T, which commutes with the enumeration of objects. So an image of the object with index n is once again an object with index n. Then we say that the category T satisfies the Fermat property if for any morphism in T and for any three morphisms x, y, and s in morphisms of T, we have an identity like this. So the difference of fx plus ys minus f of xs is equal to y times some other morphism g of x, y, and s. here plus, minus, and the product come from the theory COM-R. So we had these polynomials as morphisms in COM-R, and we have their images under the map, under the functor iota inside of the category T. So this is a valid identity on morphisms, and this is called the Fermat property. So essentially what this property tells us is that we can form Taylor expansions of morphisms in our category. That's the rough idea of what Fermat property is. And obviously the theory COM-R itself satisfies the Fermat property, because if you take a polynomial, then obviously you can take the difference between p of x plus y minus p of x, and this is divisible by y. This is a standard fact about polynomials. But this property also, of course, holds, for example, for smooth functions or holomorphic functions. So for smooth functions, this is called the Adamar lemma. And let's consider the concept of an algebra over Fermat theory. So let T be a category satisfying the Fermat property, and the model of T in the category of sets is a product preserving functor from T to sets, just as in the case of commutative algebras. And we denote this category by TL. So this is the category of product preserving functors. We denote it by TL, just as in the case of commutative algebras, we had COM-ALK. And let's consider an example. So we can consider category T equal to C infinity, where the morphisms between M and N in C infinity are just all smooth maps from Rm to Rn. And we have a functor from COM-R to T. So here you see it's a bold R, so just the ring of real numbers. And this morphism is very simple. We just consider each R polynomial as a smooth function. And this results in the required morphism for the Fermat property. And look, we actually fixed duality between algebra and geometry in a sense. So for any manifold M, C infinity of M, i.e. the ring of smooth functions, has a natural structure of C infinity algebra. Because if you have a collection of n functions from M to R, then you can plug it into a smooth function from Rn to R, and you once again get a smooth function on the manifold. So indeed, this is a model for the theory C infinity. And now the property like this holds. I mean, it's a bit of a computation, but it's not that difficult. You can start by proving it for open subsets of Rn, and then extending it to arbitrary manifolds, for example. So yeah, this is very nice, and I guess that's the main reason why we even started thinking about such objects as Fermat theories, maybe algebraic theories in general. And the same applies for the theory of holomorphic functions, denoted by O, where the set of objects from M to N is just the set of all holomorphic maps from Cm to Cn. So now we have this notion of a Fermat theory, and we want to derive it. So we want to consider derived algebras over a Fermat theory. And we have two kinds of derived algebras. So first of all, we have DG derived algebras. And to define DG derived algebras over a Fermat theory T, we consider a subcategory of commutative differential graded algebras with homological grading, and which are connected. So they're concentrated in non-negative degrees. This subcategory should consist of algebras with a structure of a T algebra in degree 0, And this is a category of differential graded T algebras. So the derived version of T algebras in the sense of like DG derived geometry. Also, additionally, here the morphisms, I guess I didn't write it, but we not only have a structure of T algebra in degree 0, but also morphisms preserve this structure. So if you have a morphism of CTGAs, it must preserve this structure of T algebra in degree 0. But outside of this, we don't impose any other requirements. And in a simplicial setting, the definition is arguably even simpler. We say that the category of simplicial T algebras is just the category of product preserving functors from T to simplicial sets. So instead of sets, we consider simplicial sets, but since the properties of the category of simplicial sets categorically are very similar to the properties of the category of sets, nothing changes, and we still can define what is a model of T in simplicial sets, and we get simplicial T algebras. And the category of simplicial T algebras carries a model structure induced by the forgetful functor from simplicial T algebras to simplicial sets. So differential graded T algebras, the category of differential graded T algebras also carries a model structure induced by the forgetful functor to the commutative differential graded algebras. And thus, it is natural to ask whether there is Quillen equivalence between the two categories. So let's look at a prototypical example of such an equivalence. So by a result of, or rather a remark of Quillen in his 1969 paper, Rational Homotopy Theory, there is a Dold-Kan adjunction between the category of simplicial commutative algebras and simplicial differential commutative differential graded algebras. So what Quillen shows is that the usual additive Dold-Kan correspondence actually induces a monoidal Dold-Kan correspondence between the categories of algebras. And it is worked out in detail for categories of Lie algebras, and it is sort of remarked for the categories of commutative algebras. But nevertheless, the Quillen strategy allows one to recover the proof in the commutative case as well. And note that N is the Moore complex functor, so we have an explicit formula for this. Just take an intersection of the kernels of differentials from 1 to n, and then G0 induces the differential on the GG side. So I guess the main result of my paper is that if T is a Fermat theory over the theory of commutative algebras over Q, then the additive Dold-Kan correspondence also induces a Quillen adjunction between the category of simplicial T algebras and the category of differential graded T algebras. And actually this adjunction is not just a Quillen adjunction, but also Quillen equivalence. And the idea of proof is pretty similar to what Quillen has. So we basically just consider Quillen's argument, and where we need to use some sort of approximation reasoning, we just use our ability to expand each morphism in a T algebra into a Taylor series. And as it turns out, homologically speaking, there is no much difference between polynomial algebras and T algebras. So yeah, I guess the idea of proof is to just generalize Coulomb's argument to algebras over T, exploiting the fact that any element F in a T algebra admits a Taylor series expansion. All right, so what can we apply this to? Well, one of the applications is, of course, the fact that structure of a homotopical site can be transported along the junction Qn, and hence various models of derived differentiable stacks are equivalent. So you can consider a model where your site consists of simplicial algebras with Grothendieck topology that is induced by, I don't know, some elaborate topology on C-infinity rings. There are actually various kinds of possible topologies on C-infinity rings. And then you can transport it into the world of, for example, DG algebras and vice versa. So actually, we describe a canonical procedure of deriving the topology on, for example, C-infinity rings or just in general algebras over Fermat theory, and obtaining a homotopical Grothendieck topology or homotopical coverage on the corresponding homotopical site. And another application is that we can calculate the value on a DG T algebra semi-explicitly. So we give an explicit formula for the adjoint functor Q, which, if you think about it, is not so explicit because at some point we need to take a free algebra over a Fermat theory, which is quite often huge, and in a sense, the real calculations still rely on, for example, the fact that you can recover the value of QA on free objects just by taking free objects in the category of simplicial algebras, but still it is somewhat of an application because you can explicitly calculate the value of the adjoint functor on your DG algebra. And I guess the final application is that we can interpret different models of derived manifolds or schemes or complex analytic spaces in terms of derived T algebras. So, for example, we can interpret AKSZ models, models of Berendt and others that were recently developed for derived manifolds. And also we can interpret Spivak's and Spivak's model of derived manifolds in terms of derived C-infinity rings, which allows for some allows to easily establish equivalence between different approaches and shows that essentially there is only one notion of a derived manifold, whatever that means, and whichever setting you work. And I guess I should add one more application here. So the equivalence that we just described also allows us to, so we can define differential cohomology on derived stacks using the approach above. So I guess, yeah, this sums up the main applications of the results obtained in this paper, and here are some references. So, of course, Coulomb's paper on rational homotopy theory, Toynes-Wisocki paper on homotopic algebraic geometry. For C-infinity rings, I guess the main reference is the book by Martek and Reyes, Models for Smooth Infinitesimal Analysis. And also there are several papers on various flavors of derived manifolds and derived C-infinity rings. And these are, the paper of Karkady-Reutenberg on theories of superalgebras of differentiable functions, the paper by Borisov and Noel, simplicial approach to derived differentiable manifolds, and finally, my paper, equivalent models of derived stacks. You can find it on arXiv. All right, I see that I finished significantly earlier than I expected, and I guess I apologize for this, but thank you so much for listening, and I hope it was somewhat intelligible.
Yeah, thank you so much for your Grisha. Are there any questions? Ooh.
Sort of a naive one, I guess. I mean, I don't know if there's anything that can be intelligibly said about this, but I mean, can you use any of these equivalences to sort of help you? Like, let's say you want to do computations in like a derived, like an intersection theory, essentially, but you have to sort of take the derived intersection product to kind of get the right multiplicity, sort of like the standard motivating problem. Because, like, you know, are there new tools on one side that can help you do these calculations, or?
Yeah, I mean, sure, because for example, if you have like some known problem for simplicial in the simplicial setting, then you can translate it into a differential graded setting, and then basically you can use absolutely the same machinery you use to calculate derived intersections in algebraic geometry. So you can take the Koszul complex and then Koszul complex, and then you can find the derived intersection this way. So this sort of shows that this procedure is legitimate. So you can indeed take your simplicial problem, translate it into the differential graded problem, apply your methods, and what you get is indeed the correct derived intersection. So yeah, I guess you have.
Can you go backwards? Like if you're starting from algebraic geometry and you have some very complicated derived intersection product, can you make it a simplicial problem and somehow use some like combinatorial simplicial tools to kind of get a handle on it?
Yeah, I guess so. But actually, I would say that, I mean, for like derived differential geometry, there is not a lot of calculations right now, but I suppose so. Yeah, but I honestly don't know, because like it's a very new branch of derived geometry. So I don't know.
The other thing I was also sort of wondering about is like, it seems like something I'm hearing about a lot of these like shifted symplectic structures on derived stacks. I'm wondering if there's anything that can be said on either of these two sides about such things.
Yeah, sure. I mean, I guess if you can, so okay. I'm not sure if there is something meaningful yet said about shifted symplectic structures for this kind of analytical stacks or stacks over the site of derived C-infinity rings. But certainly there are shifted symplectic structures in algebraic setting, and basically this machinery of Fermat theories allows you to set up shifted symplectic structures or differential cohomology, for example, as I said before, in analytic setting as easily as you can set it up in algebraic setting. So if you can define something algebraically using Fermat theories, you can define it analytically as well. That's the upshot of this approach. But once again, no calculations so far, I guess. So I mean, it remains to be done.
Do we have any other questions, or if not, I'll stop the recording and see if there's any questions for after the recording. And so, can we thank Grisha again? Yeah.